Hey there, my name is Alejandro and welcome back for day 55 of me doing the Daily LeetCode challenge until I reach 1 year's worth of green contributions here on GitHub. So today's problem is for September 9th, 2024, and let's get straight into it. Okay, today we get a LeetCode medium problem 2326, spiral matrix 4. Okay, we've seen a problem like this. Okay, you're given two integers m and n which represent the dimensions of a matrix. Right, okay. You're also given the head of a linked list of integers. Okay, we're just getting linked list problems lately. Generate a m by n matrix that contains the integers in the linked list. Wait, okay. Generate an m by n. So, you're given two integers m and n. You're not given a matrix, and you're given a linked list head. Okay. Generate an m by n matrix that contains the integers in the linked list that presented in spiral order clockwise. What? Starting from the top level of the matrix? If there are empty spaces, fill them with -1. Return the generated matrix. Okay, so you just do like one parse around the... Okay. So this is the example. So okay, it's like the linked list is 302. Okay, so it's like 30268179425. Okay, and then here you can just do the same thing recursively, right? If there's no more values, then you stop. Okay. So the first idea that comes into my mind is we can essentially do this recursively, right? Where it's like we go through the linked list to do the outer border, right, of the m by n matrix, right? And then okay, so we can do something like this. We're gonna do definite. It's gonna be self. Okay, this shouldn't be straight. I remember doing a spiral matrix problem. That gave me a little bit of PTSD because I think that was one of the problems where I spent like over 4 hours on, or maybe even over 5 hours on, because there was like some little trick where it was like the go right 1, down 1, left 2, up 2, right 3, down 3, and etc. Where I didn't realize the little trick, and so I ended up doing it like very, very gently, and that took a while. But thankfully, this problem seems a lot. Well, not that the other one was too difficult. I didn't realize the trick, but this one seems kind of straightforward, right? You essentially want to do the borders, and then from the rest, you kind of do the rest inside of here recursively, right? Doesn't matter how big it is. So first thing we can do is get the length of the linked list, right? So cur equals head. If while cur equals cur.next, and length plus or equal 1, where length is initially 0. And we can say if length greater than... Actually, wait, okay. Maybe there's a linked list length range, right? Okay, so it's between 1 and m times n. Okay, so we don't need to get the length, right? So I was going to say, like, if this is greater than m times n, return nada, whatever. But no, it's between 1 and m times n. Okay, so that's good. And we actually have at least one node, so that's very cool. Also, a little trick that my friend Noor told me, I don't think we can use it in here, but it's that 100 means n cubed. I think it was 10,000 you cannot square, where it's like you can do 1 million, but 10,000 becomes 100 million, which if it's squared, so this you cannot square, does not equal n squared. Usually 1,000 you can do n squared, and this is equal to 10 to the 3. And usually if you have 10 to the 5, so this is 10 to the 5, you can't do n squared, but can do n log n. So again, this is just kind of like hacking LeetCode here, but it's like seeing something like this, it's like, okay. But you can do up to n log n, and so we can definitely do all the way up to, okay, so m and n are each up to 10 to the 5, but m times n is up to 10 to the 5 as well, right? And if we go through the linked list, we're only going to do up to m times n work, which is at most 10 to the 5, and we know that we can do up to m times n times log of mn work, so mn kind of works. So it's like something I realized because, again, I did the LeetCode contest yesterday, and I took an absolute L, and I was talking a lot with my friend Noor, and so to kind of see like how I can do better and all these things and so on. And one thing I realized was like yesterday there was a constraint, like, you know, like d is of the power 10 to the 9, which means that obviously like I can't iterate it and so on. And so I wanted to ask him if he kind of had like any rules of thumb of like what you can do with the constraints. And he was like, yeah, generally if you see something like 100, that means you can go up to n cubed. So like something like not Floyd-Fulkerson, but Floyd-Warshall algorithm. 10,000, so 10 to the 5, usually you cannot square, so I can't do m times n squared work here. In terms of like what LeetCode can handle, right? And supposing your constant time work isn't too large, but that should be okay. 1,000 you can usually square, right? So if you get 10 to the 4, usually you can return a squared solution. So in terms of big O complexity, right? So essentially the magic number is 1,000,000, right? So this 1 2 1 2, so n cubed you can do and so on. So it's like you basically 1,000,000 is fine. Very rarely is 10,000,000 fine. Anything bigger than that is not fine, right? And so here 10 to the 5 squared would be 10 to the 10, which would give us like something like this, right? So 3 6 7 8. It's actually even worse, right? So yeah, you definitely can't do this, right? So very rarely can you get away with 10,000,000. 100,000,000 you usually can't, and so on. So even like 10 to the 4 you can't square. So just little tricks that I want to share. Otherwise, let's get straight into the computation. So ideally, okay, so here I was going to say self.m, self.n, self.m. Actually, wait, m is the rows, right? So self.n equals m comma n. So, okay. What's m? 3? Yeah, so that's the number of rows. Row count. Okay, we'll keep it like this. Self.m equals none, self.n equals none. Maybe we do self.head equals none. Equals head. I don't know if something like this is useful. So essentially we want to do a parse, right? So we want to go around the borders. Spiral borders. So you want a position. So okay, so we're going to do a position. Okay, essentially right now what we want to do is we want to traverse the linked list, and we're going to go 0 1. So 0 0 0 1 0 2 0 3 0 4. So we need kind of like a range, right? Essentially we need corners, right? Corners. Assert length of corners is equal to 4. So we're going to do self.spiral borders. So essentially the point is that I want to go around these borders, right? Okay, the very first thing we should do is do this. Self.matrix is equal to none. And we're going to say self.matrix is equal to a number of rows, right? And so how many rows? So for this in range, self.n, right? And each row is going to have this many elements. So -1 times self.n, right? Or we can do this, -1 times self.n for this in range self.n. We can even call this like this. But for the sake of consistency, we'll do it like that. Self.matrix, so we initialize everything to -1s. Why? Because it says like any empty spaces, you fill them with -1. So at any point, if head if we're done populating the elements from the linked list, everything else wants to be -1, so we're done, right? So essentially at this point, so the corners is going to be very easy, right? Actually, I'm going to take in a top left, top right. I'll even call them like this: top left, top right, bottom left, bottom right. Let's literally call them that. or you know what, corners equals corners. Assert length of corners is equal to 4, and there we go. Okay. TL, top right, bottom left, bottom right is equal to corners. Okay. Or I'll figure out which one I want to comment off. But the point is this, right? So the idea, so okay, I'm just rambling at this point. The idea is that when I want to go around the border of the n by n matrix, right, just once and populate the head from there. At any point, if head if there's something in head, then I just return the full matrix, right? Otherwise, spiral borders, what we'll make this do is it'll go through the first borders, right? If at any point if head is empty, it will return the full matrix. Otherwise, it will recursively call itself with the new 4 corners, right? And so the new 4 corners are essentially from this one, go right and 1 below. From this one, left and 1 below. From this one, 1 above 1 and left below. And from this one, up 1 and to the right 1, right? Also, if top left is equal to like bottom left, that means we're like in the same row, like, or just one row, and then same thing with the columns, I mean just one column, but it should be fine, right? Yeah. If top left equals case 1, only one row, one column. Okay, assert top left of 0. So this is 0, 0. We want to make sure that the top left is above or equal to the bottom left. Bottom left of 0. Assert that top left of 1 is, so that's the column, so less than or equal to bottom left of 0, top right of 1. Assert that top right of 0, 0, top right of 1, top left of 1, which we already have, so let's skip that. Assert bottom left of 0, so that's this row value. It's going to equal to top left of 0, which we already have. Assert that bottom left of 1 is less than or equal to bottom right of 1. Assert bottom right 0. It's going to equal to top right of 0, which we already have. Assert bottom right of 1 is greater or equal to bottom left of 1, which we already have. Okay. So we only need 4 asserts really. Okay. Sorry. Right, if I do Python 3 1,2 equals 2,1 false. Do this backwards. Yeah, okay. Sure equals top right if not self.head, return self.matrix. Otherwise, we're going to say self.matrix, we're going to say x comma y is equal to top left just any one of them, right? Self.matrix at x comma y, head.val, assert head.next is none, return self.matrix. Right? Okay, so that's the case where we have just one row and one column, i.e. only one box, right? Either head is already filled out, in which case we don't need to go anymore, it's just -1, or otherwise there should be one value for us to put, self.matrix of x, y, so at that coordinate, we put in head.val, assure that that was the end of the linked list, because again, it should be of length 1 to up to m times n, and then return self.matrix. And so there we go. Case 2, one row. Case 3, one column. Case 4, more than 2 plus rows, 2 plus columns. Multiple rows, multiple columns. All right, there you go. Okay, so so one row means that, like this, the top left and the top right, if top left, the y value, right? So the column, oh, wait, I got it, no. So this is the row value, is equal to top right of 0. No, bottom right. Bottom left, I mean. Or top right of 0, right of 0. Assert that they're both true, i.e. there's only one row. So this is just to make it easier for debugging. Assert that they're both true. And here there's just one row, right? So this is going to be a very easy case. Just one row. So go from top left to top right until done. Right? So for x is equal to top left of 0. For y in range, top left of 1 all the way up to top right of 1 inclusive. If not, self.head, then self.matrix. Otherwise, we're just going to say, again, self.matrix of x and y is equal to head.val. And then, there we go. So if not self.head, and then head equals head.next. Self.head equals self.head. Let's make sure we do our self.heads up here. Self.head, self.head. Okay. So this is just the one row case, right? So we go through each y. Not head. You know what? We have row comma call equals 0 comma 1. Here are all the zeros. I'm going to replace them with row. All the ones with call. 0 comma 1. I hope I didn't. Okay. Right. Case 3. Here we're going to do an elif just in case. Elif. So here we're going to have something similar, right? So let's just copy this. So now we want top left row, bottom left row. Now we want to make sure that if top left and top right have the same column, right? Or bottom left and bottom right have the same column. then assert that they're both true. And then, so we just have one column now, right? And so we essentially, this time we have our y value fixed, which is going to be equal to top left of call for x in range. So we want from the top left, which is the same as top right. So top left of call of row all the way to the bottom left of row, which again, bottom left and bottom right are the same. Right, there's only one column. I hope I'm doing this right. But otherwise, if not, self.head, return self.matrix. At any point, if we're done, we return the matrix. Self.matrix otherwise of xy is equal to self.head.val. Self.head equals self.head.next. Otherwise, assert that top left of row is strictly less than bottom left row. Assert that top left, you know what, we're gonna do this. Instead of less than or equals, we're just gonna have strictly less than signs. Less than. Less than. Right, so now I want everything to be the same, right? Top left is strictly above bottom left rows. Top left column is strictly to the left of the top right one. The top right is strictly above the bottom right. Bottom left is strictly to the left of bottom right, right? Yeah. Okay. Multiple rows and columns, right? So just assert the else clause essentially. Otherwise, we can also do every possible coordinate in order, right? So essentially we want to go from top left to top right first, right? So we want to go from top left, so okay. Okay, one thing as well. One thing I want to assert though is that top left row is equal to top right of row. Really, I just need 2 rows and 2 column values, right? For the 4 corners, but oh well. Assert bottom left row was bottom right row. Assert that so top left and top right, so now we want columns, right? So top left column equals bottom left column, and assert top right's column is the same as the bottom right's column. So that makes sense. Right, so again, we keep getting corners and so on. So I'm just doing all these asserts as sanity checks so that like if I have a bug, it'll be much easier to check it out later on. Multiple rows and multiple columns. So, okay. Now we want to go one from top left to top right. Then we want to do top right to bottom right. Then 3 we want to do bottom right to bottom left. And then 4 bottom left to top left, right? And maybe each time we can do -1 here, right? -1, -1, -1. So here, instead of going all the way, I just do all the way up to the last one. That way, when I do this column, I do everything except the last one. That way, when I do this one, like I don't repeat the corners, right? And then yeah, from this, okay, so that makes sense. So okay, so first do top left, step 1, top left, top right, -1. Steps are step 1. Okay. The row is equal to the top left of row. Right? So top left and top right. I'll put these again just in case. Right? But otherwise, top left of row is equal to top right of row, right? So my x is equal to top left of row. For y in range from top left of column all the way to top right of column -1. Don't include the last one, right? So that way it's like I do all the way up to 6 here, and then when I do this one again, I won't have done 8 before, so it's like I won't double check it, right? So otherwise, I'm gonna say, if not head, self.head, at any point, if we've exhausted the whole linked list, we return self.matrix. Otherwise, we're gonna do self.matrix of x, y is equal to, also I gotta make sure that they're all in bounds, right? But they should be, right? Anyways, self.matrix, because of the way I'm gonna feed in the values, but otherwise I'll put in asserts, and there we go. If not self.head, yeah, so this is self.head.val. We're gonna say self.head equals self.head.next. There we go. Otherwise, step 2, we're literally just gonna do this a whole bunch of times. Step 2 is top right to bottom right. So now let's do this. Let's get rid of this. So let's get this as a reference point. I'll add that for later here. So we know that bottom, you know what? It's a good thing to put them in each of these guys, right? So let's just assert that here. Let's assert this guy here because why not? It's just useful. They're asserts. The whole point of asserts is that they shouldn't be remain. But the point that I checked them before is why they're not needed, but there we go. Top left, top right, row is the same, so there we go. Otherwise here, and again, we'll just do step 3, step 4. Step 3 was, there we go. Step 4. There we go. Okay. So these are rows. These are columns. So I want bottom left row. All right. So from bottom left. Wait. No, I want from top right to bottom right. Right. Okay, I want the asserts in a different order. Top right to bottom right. So I want to make sure that essentially top right is equal to this one. And I might have these mixed up, but I'll change them if need be. But otherwise, my y is equal to top right of column. All right, top right. So essentially, I'm at the top right. I want to go down to the oh, okay. If it's 1, right. Okay. Okay, I know it's just a lot of work all at once before running, but this should all work once I'm done writing this, right? It's just a lot of tedious code, and it doesn't mean that like, it's super inefficient. It's just like, it's like, you know how like if you have to do O of 4 n work and you write 4 different O of n for loops, it's as if though you wrote a, you know, one for loop that iterates 4 n times, right? So that's kind of what I'm doing here. Well, instead of 4 times n, it's 2n plus 2n. Okay. Bottom right. Yeah, so I'm in here. Step 2, top right to bottom right. For x in range from top right row to bottom right row, and that's the same thing. Then this is essentially the same spiel, right? So bottom right, because maybe I have these in reversed. So x is equal to, so now we want to go from the bottom right to the bottom left, right? Is equal to bottom right of row, right? I'm on this row. Whether I'm at the bottom right or bottom left, it does not matter, right? The point is that it's the same row. Then we're gonna do for, but that's not the point. I want to go from bottom right to bottom left. So I want to traverse through the columns. Wait, this is not making sense. No, it is. No, I do want to traverse through the columns. Yeah, so I'm on the same row. I want to traverse through these columns. Okay, that makes sense. I need to make sure I don't trip myself here too much. So let's do one like this. Let's go here. So top left, top right. Nice one. You know what? Let's do this. Bottom left. Okay, but now we gotta be careful. Let's do bottom right here. Bottom. Okay, so let's make sure that they're equal. But now we want to go from the bottom right. So we want to go from, okay, we got to be careful because now we're going from right to left. We're not going left to right. So we want to go for y in range starting from the bottom right column value and going downwards all the way up to, so actually we want to, no, we don't ignore the first one, right? That's the point. We went all the way up to this one. We don't want to ignore this one, right? Then we want to go all the way up to this one. So bottom left of column. Now this, if we want to include it, we would do -1, but the point is that we don't include it, right? So we go up to it and not inclusive, and then -1 as our stepping. So we're going to go from essentially this value to this value here. And now we do the whole thing again. And now is the last one. Okay, I just got to make sure I don't confuse myself at the time. So when we're going to go y is equal to bottom left of column, right? So the same column is just we're going to traverse through the rows. Here we're going to do for x in this guy's range. So now we're going to do bottom left. The bottom left row all the way up to, again, this is a larger value. So we're going to do stuff by -1 increments. And so we're going to do up to the top left row. Not inclusive. Otherwise, at this point, we just finished populating the border of the m by n matrix. Since we haven't returned yet, if not self.head, and self.matrix. And still elements, if done, return. Still elements left to be populated from the linked list. We will do this by recursively calling this function within the inner m-1 times n-1 matrix from here. New top left is equal to top left of row, so we're gonna increase that by 1, right? Top left of column, so we're gonna increase that by 1. New top right, we're gonna do something like this. New top right. So top right, we want to go -1 in the columns. So -1 in the columns, and then +1 in the rows. So that works out nice. So new bottom left. Is equal to something like this. Bottom left, row and column. So from the bottom left, we want to go -1 in the rows. And we want to go +1 in the columns. And then for new bottom right, we do essentially bottom right of row, bottom right of column. From the bottom right, we want to -1 for the columns, so -1, and then this will be, for the rows, we want a -1, so -1. We're going to do new corners is equal to new top left, new top right, new bottom left. Return self dot, Jesus, this is a long function. Spiral borders. What? Populate border from corners. Populate border with corners. Self.populate border with the new corners, right? So essentially it's like we have populated this full border here. Now recall the algorithm recursively with the new inner matrix, right? I wish there was a better example because this just happens to be one row, but like the top left and bottom left will now be the 0. Top right and bottom right will now be this -1, and so we will recursively call it with the rest of these values here, right? But the point is that like we do the border of the first full n by n matrix, and then once we're done with that, we recursively do it for the remaining stuff that's inside except the borders, right? So that's kind of how I'm doing it. It's like, imagine you're solving a puzzle, and you're solving the puzzle and you do all the borders of the puzzle, right? And then imagine like from then on you do all the inner side borders, right? So it's like if there was n by n total pieces, the inner size is like now m-1 times n-1 total stuff. And so I hope that kind of makes sense. But return self.populate border with new corners. And that's essentially it. So for now, we can make this call, return self.matrix, right? Just for testing purposes. So here we're going to say corners equals 0, 0, 0, so row 0, column all the way up to self.n, -1. Then here we're going to have self.m minus 1 comma 0, and then self.m minus 1 comma self.n minus 1. Self.populate borders border with corners. Let's see if that gives us everything except a 0 here. -1. Right, that was when I was doing the control F from before. So let's see. So there's a lot of stuff that's not good. Ooh, I gotta be careful, right? I need to do, okay, top left is equal to, I need to make sure that I pass them correctly. 0, 0. Top right is what? 0, self.n minus 1. Bottom left is equal to self.n minus 1. Zero. Get corners, get initial. So why is this the case? I do 302. Print case 1. Case 1. Here we're going to do case 2. Case 3. Case 4. So we're in case 4. Good. Very good. Print string top left equals. Okay, how do I populate the? How do I grab these? Top left, top right, bottom left, bottom right. Bottom right equals 0, 1, 2, 3, 4. Okay, good. 0, 1, 2. So yeah, so this is 2, 4. This is 2, 0, right? So I go, so x is equal to top left of row, 0. For y from 0. Oh, you don't include it. So if I do this, I don't include it already. If I do this, I don't include it already. And in these cases, I don't include it already. That I got it covered, that I got it covered. Now let's try this. So now I'm just missing the 0. Okay, so that was a small logical bug. And then the rest should work if I do something like this. Okay, let's submit it. All right, exciting. Ah, ¿qué pasó? Where's my assertion error? here, case 4. I want to print this right below case 4. Maybe I just hard code the cases where there's one row and one column, or one column. Or just if that's the case, then like, okay, bro. But that's what I'm doing here. Let's look at here. M and N. Yeah, they're both at least 1. So okay, so when I ran this, I have M equals 10, so there's 10 rows, 1 column. So there's 1 column. So yeah, there's 1 column. So essentially I'm getting into case 4, 1 row, 1 column. Top left column equals top right column. That's true. Bottom left column equals bottom right column, which is also true. So why am I not stepping into this else if case? Oh, I do. It's just that then from here. Okay, really I should have this all as an else. Right. Okay, so another one is breaking. So let's print these. Top. Okay. So I'm here. Top left column should be less than or equal to top right column. Why the heck do we have negative values in here? Okay, so when I recall the function, I gotta be very careful, right? So okay, so bottom right. So yeah, bottom right. Okay. I gotta be careful with these corners, right? So yeah, so you don't draw example 3. It's like top left becomes 1, 1 now. Top left, top right, subtracted a column, and down 1. I want to print another thing. are we already done with the problem? We are not. Does it not show me an expected result? What was the expected result? Return empty list for now. Okay. Worst case. Okay, I was gonna say we can hard code a case. Okay. I just gotta think of this. We just gotta take care of the cases where we have one row or one column a little bit better. So I'm trying to think in this case, where can we fit the last one, right? Print self.matrix. Thanks, we're just missing one. I wonder if we do the two cases first. Self.end equals 1. There's only one column. Only one column. So one entry per row. Close this. Append another list with head.val head equals head.next. Return res. So now something like case 3 should pass. Okay, let's do same thing for one row. Actually, let's submit and see if we fail the one row case, right? Which we should. Okay, prints, we're gonna change those to hashtag prints. There we go. But we should fail the one row case or no? Okay, we don't. So it's only, we were only messing up when there was only one column. Well, okay, first of all, great that we solved it. So, okay, there's a peak right about here. I guess people were solving it there. Okay, cool. Again, that might be when there was less tests and so on, but okay, so the big distribution is around here, so that's very good. Awesome, so we solved the problem. I'm trying to think, why does it only work? So if there's one column, but it works just fine when there's just one row. There's one column. I wonder if we can do something like this. Is it just the one test case, or is there more? So yeah, n equals 1 again. Equals 1. Turn empty. So if I do something like this, there's only one m. I don't know, it's just bizarre. Oh. Okay, that's why I accidentally changed this like that. Do this for y in range, top left, this. Bottom left. Include it, right? So we were just missing by 1. So now we can probably get rid of this. So okay, we were doing it correctly, it's just we had a logic bug. Okay, there we go. And now we submit. There we go. Okay, 90%, excellent, and so on. Okay, so we just had a little logic bug, right? So essentially, so we have the case with whatchamacallit. So we covered the case when you only have one row, one column, i.e. just one square, right? And that's fine. We do the one row case, right? And so we go from everywhere. So since there's only one row, right? The top left and bottom left are essentially the same row. Top right, bottom right are essentially the same row. So you only go from the top left's column count to the top right's column count, right? And so here, like from top left's column all the way to top right's column, but you got to include that one, right? Because that's part of the solution. So +1 here. I just forgot to put a +1 here when I did the one column case, right? So that's why I was failing that one. So yeah, so that just makes sense. So we got rid of that. Essentially now we can get rid of pretty much all of our asserts. Okay, I'll at least keep the ones that I think are useful. I use all of these. Get initial corners. Okay, so we have this. Assert those are equal. Make these asserts right here. Consistency check. Relationship checks. One row and one column. That makes sense. So we have a lot of this repeated type of code, but it's kind of needed. Dot head equals self dot whatever. This is fine. One row. We do this and get rid of this guy. Just one call. So go from to bottom left until done. Okay, case 4. Only one position in matrix, so take care of it. That one's self-explanatory. This is also self-explanatory. Stronger relationship checks. Gonna get rid of these guys. These are the steps. I have them lifted as here. Get rid of this comment. Step 4. Don't need double spaces here. With the problem, return. Okay, no problem. If done with the problem, return. Okay, so yeah, new bottom rights. Get rid of this, get rid of these lines, and there we go. Okay, so very long solution, albeit a correct one still. We can resubmit, and there we go. That's pretty much all. We might not get 90% exactly again, but there we go. 85%, we beat most of the crowd. Very good solution. Again, there's a lot of code, but essentially, like, you'll see, like, a lot of these codes are like very identical. And it's just, I don't do any more work than what's needed to do, right? So it's like, for something like going around the border here, instead of having one loop to do it all, I essentially do one loop to go through here, one loop to go through here, one loop to go through here, and one loop to go through here, right? So that's essentially like all I'm doing. So even though I have a lot of loops and so on, the actual computation is as optimal as can be, right? I don't loop over any element twice or anything like that. So otherwise, I'll kind of explain my solution. So again, the problem was I give it a head of linked list, right? And you kind of want to populate an n by n matrix in a spiral way, kind of like the way that is shown in this picture. And the number of nodes in the list is up to m times n and at least 1. And again, the length of the matrix is m times n, right? And it says that if you, at some point, if you run out of elements in the linked list, right? So it's not like up to n times n, then populate the rest with -1s, right? So that's what I do at the very beginning. The very first thing I do is I populate my matrix to be of m times n in size, and everything is -1s, right? And so that way, what I can do is populate the linked list until there are no more entries to put in, and then return the matrix because the rest have already been populated with -1. So that's the very first thing that I do, right? And the idea was this. Okay, so given a thing like this, our matrix currently looks as -1s, right? So let's draw this out. So here we have a matrix here. And the very first row is going to be -1, -1, -1, -1, -1. Let's do this multiple times, and there we go. Now the very first thing I'm going to do is I essentially have head is equal to this thing, right? And here, just in case, m equals 3, n equals 5. Right, but the point is this is the number of rows, so 3 rows, and then 5 column entries per row, right? So that's essentially the problem we have. So initially I set everything to -1. Then what I'm going to say is, okay, you know what? We can also do a 5 by 5 example in case that's more useful. Right? So essentially all I'm going to do is, you know what? Let's also double the number of elements in here, right? So let's just do that. You know what? Let's make this a 7, 4, 1, 3, 2, 8, 6, 6, 9, 1, 5, sure, 7, and 8, right? So random values here. Okay, the way that we're essentially going to do it is the very first thing I'm going to do is say, hey, okay, why don't we populate the borders, right? So these are the borders right here, right? So from here to here, and then from this element here all the way down up to here, then other ones over through here, and then up over here, right? So this, then from here this, then from here this, and then from here this, right? And so the way I'm going to do that is essentially I'm going to say, hey, I created a function that is able to populate the borders of this self.matrix, right? So the way it works is I give myself 4 corners that I want to traverse from, right? At the beginning, it's going to be this value, this value, this value, and this value. And by these 4 corners, I know that this is the border that I want to arrange, right? And the idea is that once I populate these borders, then I can essentially create my new corners to be here, right? The inner matrix over here, right? So this is kind of the inner matrix. Oh, sorry. The inner matrix is over here, right? In fact, let me make these zeros just to make it clear here. If I make these zeros, right, just for the sake of showing, this is what I mean. Tac, tac. Tac, tac. Right? You know what? Let's make them negative zeros for now, just to get everything nice and consistent. But so that you can still get the point. You can see that like these negative ones kind of represent the border of the matrix, and these negative zeros, they're kind of like the inner matrix, right? So the way I can do this is I can populate the borders here, like such, and then from then on, populate the whole matrix the same way recursively, right? Because what's going to happen is I come through here in a spiral, and a spiral, and a spiral, and a spiral, and then I end at this element here. But how do I continue from this element? I go through here, down here, up here, and then here. And then the same thing over and over and over here, right? So from this element, this is going to be the next one I go to. But I'm going to essentially do the exact same thing for this inner matrix of negative zeros in here as I did here, right? Go through the first row, then this column, then this row backwards, and then this column backwards, right? And I'm just going to do it the same way inside each inner matrix. So that's essentially what I'm doing. So to put it into example with this example here, the very first value that I have is 3, so I'm going to set this to 3, and I'm going to get rid of this one in the head, right? So head equals head.next, right? At any point, if I have no more elements in head, what you'll see is that I will essentially stop. Then the next value here is 0, and so I remove that from head. Then I'm going to come in through here. This is going to now be 8. Oh, sorry, this is going to be 2. I get rid of it here. This is going to be 6. I get rid of it here. This is going to be 8. I get rid of it here. I wish the negative ones weren't that. You know what? It's you know that so let's say x is equal to -1, and let's just place negative ones with x's here, so that it just looks much more clear. X's. Okay. Now we've done this first row, right? So from this first row, okay, so I should put this back. Essentially the way I do it is I do up to this. That way I can do this full column except the last one and the whole thing and so on. But for explanation purposes, it's kind of the same. Essentially now I'm done with the first row. Now I'm going to go through this column, right? So from here, I'm going to make this a 1, head equals head.next, make this a 7, head equals head.next, make this a 9, head equals head.next, make this a and then I start from here. I essentially populate this column. Then I'm going to do this row, right? And I'm going to do it backwards. So we're going to set this value now to 4, and we're going to get rid of it here. Head equals head.next, set this to 2, head equals head.next, set this to a 5, head equals head.next. This is equal to the current value of head, so this is a 5, so 5, and then head equals head.next, then 0, then actually x. Now we've essentially done all of the last row all the way up to the last element. So from here, I now do this one. Again, in my logic and so on, I do all of them except to the last element to make things easier, right? So it's like, that way if I do all this, when I do this column, I can start from this element without having it done it twice, right? Otherwise, I could essentially go overlap through them, and then like, you know, I don't update head equals head.next, so when I reset this value, it sets it back to 8 twice, but I just don't do that, right? I just ignore the last element every time, so that way it's like I don't have to reset it twice. But otherwise, now we go up to this column, and so here we're going to set this to 0, head equals head.next, this is equal to 7, head is equal to head.next, this is now going to be equal to 4, and head equals head.next, and this is going to be equal to 1, and head equals head.next. Now here's the tricky part. We now check if head is none. If head is none, that means we're done with the linked list and we've done populating, right? At any point, by the way, whenever I was populating these values and I was saying like head equals head.next, if head is no more, then I return the matrix, right? Because these x's represent -1s, and we know that if we're done with the matrix, we want the rest to be -1s, which they already are anyway, right? It's just I'm writing x so that it's kind of like cleaner in terms of the matrix for showing my solution, right? But at any point, if we've exhausted the whole linked list, we are finished. But otherwise, if we're at this point, right, and we've finished the full initial border of the n by n matrix, and we're still not done, there's still elements in the linked list, we call this function recursively, right? We now do it with the inner matrix that's in here, right? That's essentially what we do. Well, I also have special cases where it's like at any point, whenever I call this function, if there's just one row, I handle that case like on the side. If there's one row, one column as well. If there's only one column, I handle those as well. But again, those are only easier versions of this problem, so I might as well showcase how I do this one, and then the other ones are kind of trivial, right? If there's just one row, then like, you know, just populate all the values from that one row, column by column. Otherwise, if there's just one column, then populate them all from that one column, and so on. It's only it gets harder when there's more than one row, more than one column, so that's why I'm just showing that case. But otherwise, essentially now, this 3, where this 3 is, where this 8 is, where this 4 is, and where this 0 is, used to be our 4 corners, right? These were the 4 corners that we had passed into this function, populate border, right, with corners here that we grabbed the 4 corners from. And we essentially, this was what helped us denote which border to populate, right? Because again, the whole point is that we're going to call this function recursively, so now we can do the same thing for the inner quote-unquote matrix that is of size 3 by 3 here. So it's actually n minus, so where I had this is actually -2 and -2. Okay, but now we have this 3 by 3 matrix that we're going to do the very same thing for, right? And so the way we're going to do it is we're going to start from here. So this top left was our old top left. Our new top left is this one. This used to be our old top right. Our new top right is this one. This used to be our old bottom right. Our new bottom right is this one. This used to be our old bottom left. Our new bottom left is this one. So now we have access to this corner, this corner, this corner, and this corner over here. And that's what's going to help us delineate how we're going to recall this function. But for now, this inner matrix, right? And so we're just going to continue from there, right? Remember, if we're at this one, so like this one that we just finished from, the next one that we go to is the right one. So again, it's the very same subproblem. So here we're going to set this to a 3, head equals head.next. We're going to set this to a 2, head equals head.next. We're going to set this to an 8, head equals head.next. We're going to set this to a 6, head equals head.next. We're going to set this to a 6, head equals head.next. We're going to set this to a 9, head equals head.next. And okay, I actually had too many elements in head. So you know what, let's just get rid of them all except one. We're going to get here at 1, head equals head.next. There is nothing left in head, right? So here we return from the problem, right? At most, there would be 2 more elements left, which I can also do the case of. Essentially, if there's 2 more elements left, like, you know, at any point, if there was nothing left in head, like here, we would return the problem, right? And these are -1s and we would actually be done. Let's say, for the sake of test cases here, that head actually still has 2 elements. Here, essentially, we've done this, we've done these, we've done this, so we continue until we're done. So we set at 2, head equals head.next. But now we've populated this border over here, right? So then we're going to update again our 4 corners, right? So my top left now becomes this. My top right now becomes this. My bottom right now becomes where this x is. And my top left, my bottom left becomes where this x is, right? Now notice, this problem no longer has more than 1 row and more than 1 column, right? But this one is kind of trivial, right? It's just, there's going to be 1 element, and so you just set that element to whatever head is, if head is not none, and then just return from there, right? And so that's very easy. So that's what I mean by, like, if there's just 1 row or 1 column, or just both 1 row and 1 column, the cases are more trivial than others, right? If there's just 1 row, right, like, let's say it's like, it was this full row for some reason, you know, and there's 3 values inside of head, then all you're just going to do is go through this full row and populate it by head and so on. So these cases are more trivial because there's no spiraling order to it, right? It's just, but that was the case. But otherwise, like, since head is still going, we would recursively call it with these new 4 corners, which are now the same. And then this, there's only 1 value, we set it to 5, head equals head.next, we're done. And so there's nothing left in head, so we return the spiral matrix, and that would have been what was 1 in that case, right? So that's kind of how it works, and I hope that that makes sense. Yeah, otherwise, it's pretty much it for this video. In case you want to do something similar to what I do, the extension that I use is called LeetSync. I trust this extension, but by no means does this mean you have to trust this extension yourself. Essentially what these guys do is whenever you submit a problem here on LeetCode, it'll automatically put a copy of your solution into your GitHub repository. So this problem was called Spiral Matrix IV. You'll see that I submitted something 13 minutes ago, even though I was not on GitHub 13 minutes ago. And it'll essentially put a copy of the description to the problem as a readme.md file the very first time you submit. And every time you resubmit a new solution, it'll put a copy of your most recent solution here. And so, again, there's a lot of code here, but I hope you understand that, like, it's not actually any more inefficient and so on. And that's why we're getting something like 85 or 89%. Because, again, it's like, you know, in the inner case, it's like one for loop for the top row, one for loop for this column, one for loop for this one for loop for this one. Or if it's like, you know, there's only one row, then only one for loop, and then if there's only one column, then only one for loop, and then it's like if there's only one, then do that one. And so it's like each of those cases, you know, if they happen, we'll have like the optimized amount of code in order to solve it, right? It looks very, very bloated code wise because, again, I do all of that stuff, right? And yeah, I could also get rid of a lot of these asserts. These asserts essentially check like random things. So it's like, so like, you know, like make sure that the top left and top right, you know, like if this is my top left and top right, make sure that they're the same row, right? Just consistency checks. It's like this bottom left and bottom right should be the same row. This top right, bottom right, they should be the same column for sure, and so on. Then relationships checks as well. So it's like this top left and this top right and so on. Wherever they are, it must be that, like, you know, the left one is at least equal to the top right one in terms of columns, right? It cannot be that the top right is to the left of top left, right? Because it does not make any sense. So it's just like consistency checks like that, right? So like, for example, yeah, so like top left's column value must be less than or equal to top right's column value, right? It cannot be that this is happens to be greater than, right? That means that the column value of top right is to the left of, like, the whole point of the word left is that this is supposed to be to the left of the right one, right? So if the right one is to the left of the left one, that doesn't make any sense. So it's just like little checks like that of assertions and so on, so that, like, if I had bugs, it would be very, very easy to catch what's going on. So that's essentially it. And we did. And so that's how we were able to find the right here in the one column case, I didn't have the +1 and so on. So again, like, that's why these asserts are very, very useful. I was able to find that, like, extremely quickly. Because, again, I just have a whole bunch of these asserts and so on that tells me what's going on and so on. So that's just very, very helpful if you adopt a asserts-based driven programming. But yeah, so I think I was talking about the LeetCode LeetSync extension. So yeah, it's just useful in case you want to do something similar to what I do, but always do your own due diligence before you trust a random guy like me on the internet. But otherwise, that's pretty much it for today's video. So if you did find it useful or enjoyable, I would highly appreciate if you left a like or a comment. As I say in all my videos, if you do leave a comment, I promise that I will respond to you every single time. I love reading what you guys have to say, but don't feel pressured if you don't want to leave a comment. But if you do, I promise that I will reply. So if you want to have a conversation with me, that door is always open. But otherwise, that's pretty much it for today's video, and I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye bye.